Okay, we're going to wrap up here chapter 2, and then we'll go off to chapter 3 and all that good stuff. All right, so last time we talked about really conversions, conversion factors, dimensional analysis. Remember that when we have an equality like a foot is equal to 12 inches, we can write two conversion factors for it. And they're really just fractions here where we could kind of put one unit on top and the other on the bottom. When we show our work, we do want to use conversion factors, dimensional analysis to show all the units throughout our calculations. So again, we want to know how many feet. We would use the conversion factor to put in opposite direction. The one we want to get, that's what will go on the bottom here. And obviously the unit maybe we're ending with here will go up on top. The units on top and bottom will cancel. Always opposites will cancel each other. And be, hey, you're going to do one more conversion as well. Feet, to get rid of feet. There's say 5,280 feet in a mile. Again, by setting it up like this, we can clearly see where those units are so that everything cancels correctly. We do multiply across the top. And again, come back and divide by what is on the bottom. And remember, when we do use conversion factors that come from equalities, they be considered exact numbers, and they may not be considered exact numbers. So remember that if you're using sort of an English to English conversion, it would be considered an exact number, so you don't have to worry about it in terms of significant figures of your answer. If you're doing some type of metric to metric conversion, same deal. You don't have to worry about the significant figures there in those conversion factors. But remember, though, if you do kind of cross over from English to metric, with the exception of a few that we talked about, like the 1 inch is 2.54 centimeters, the 453.6 grams is a pound. If you do cross over, you should look at the significant figures that there are in those conversion factors. And usually when you use a conversion factor like that, significant figures, there should always be probably one as one of the numbers there, and then another number, and it is the other number that you would use and look at in terms of the significant figures. Probably most of the time it will kind of default back to that original number, but not always. So you want to make sure that you do look at it. We want to always show our work this way, and that is, again, what it means, obviously, to show your work. Any of that stuff there. All right, so last thing that we got going on here in this chapter is density, and density is defined as the amount of matter that's present in a given volume of a substance. The differences in density determine whether or not, for example, an object will sink or float in water. Is more dense than water, it will sink. If it's less dense than water, it will float. Now, density for the most part has two units associated with it. Grams per milliliter or grams per cubic centimeter is typically the units that we see for density. And the number always stays with sort of the grams part, and it's always 1 milliliter, 1 cubic centimeter as sort of the bottom part. Density of liquid water, which is a value that you sometimes need on longer journeys, and you should know, is 1 gram per milliliter. You should also know that in reality, that density does as the temperature changes, so does the density value. But I would say in most cases, if you come across any type of problem, like in a book or something like that, and you kind of like need to use the density of water, most people will just use 1 gram per milliliter. But it actually will change with temperature. So density has a formula. Maybe it comes. There it is. So density's formula is mass over volume. So it is a formula you need to know. Density is mass divided by volume. What would be? ways that we rearrange the density formula. We do solve for a lot of these things, all three of these things along the way. Some people will remember it as like the DMV triangle. And density is mass divided by volume. Mass is density times volume, and volume is mass over density. So sometimes that's the way people will sometimes remember it. As I mentioned before, grams per milliliter, grams per cubic centimeter are very common units, typically for liquids and solids. Occasionally, and we won't get too much into it in this class, but you will in the next class. For gases, typically density of gases are given to grams per liter, typical units. But grams per milliliter, grams per cubic centimeter is probably the two units that we will see the most. Also, a reminder again that 1 milliliter is the same thing as a cubic centimeter. Basically, it's a 1-to-1 conversion in that sense. So, like we did in the lab last week, we take some length measurements there. The length times the width times the height, and that'll give us our cubic centimeter sort of volume. Obviously, we could just take a regular volume reading if we're just looking at something like a cylinder like you did before. I try one here. Block is 25.3 cubic centimeters. Its mass is 21.7. What is the density? So take a moment or two and calculate that up. Okay, so let's take a look at it here. Obviously, we're looking for the density, which is our mass divided by volume. Here we do have the volume given to us at 25.3 cubic centimeters. We do have the mass at 21.7. So putting that into our equation, since we have both of the things that we need. We will end up with 0.858, it looks like. Remember, the units here will not cancel out, so the number stays with the grams part, and it's 1 cubic centimeter on the bottom. Here is 3 significant figures because we're dividing 3 significant figures. So that is what we should end up with. Question on that one. Now, as we talked about when we did the lab and also a second ago, there's really sort of 3 ways that you could get a volume of sort of an object. Like I said before, you could really just sort of take a volume reading. Could also, again, do the length measurements as we talked about. The third most common way, kind of like what you did with the stopper last week, is volume by displacement. So when you put some type of solid object in some liquid like water, it will basically displace a volume that's equal to its own volume. So as we can see here in this tank, before she jumps in, we have an initial volume of the water. After she goes for a dive, we will have sort of the final volume, basically, of the water. And again, it is that difference between those two that's really the volume of the object, or her in this case, that jumped into the pool. So the volume of the object very easily can be found by doing that procedure like you did with that stopper, and just taking the final volume minus the initial volume, and that will get you the volume of the object. So I would say for density, that's a super common way to figure out the volume of an object. Just needs a little bit of water, and if it's a solid, very easily you could just drop it in there. Hopefully this is also stairs so she could climb out, but she won't be in there all day. All right, let's take a look here and see. Good look. Let's go back and look longer. Student fills a graduated cylinder to about 25 milliliters, then drops a solid in it. The liquid to 33.9. If we have the mass of the solid at 60.5 grams, what is the density here? So take a few minutes there. And okay, so let's take a look. So we basically got a graduated cylinder. We have initially filled to 25 milliliters. We have the solid we're going to throw in there. When we do so, we should see the liquid rise there with the solid in there, and it will rise to 33.9 milliliters. And obviously here we have the mass there of 63.5 grams. So from this is obviously volume by displacement. And find the volume once again by taking the difference between the volume levels there in our graduated cylinder. So the volume of our object here is going to be our final volume of 33.9 minus our initial volume of 25 milliliters. And if we do that there, going to give us 8.9 milliliters. So now we have our volume, we have our mass, so that's going to allow us obviously to calculate our density. So we could plug it in at 63.5 grams divided by 8.9 milliliters. And that's going to give us a density of 7.1 grams per milliliter in this case. Any questions on that one? Significant figure wise, I ended up with 2 based off of really the first part of the calculation, right? So here we were actually subtracting. So we're looking at decimal places. So it should go to 1 decimal place, which is correct. That has, though, 2 significant figures, which is important when we come down here, because then it's 2 significant figures divided by 3 significant figures means that my answer, again, should end up with 2 significant figures. Yeah. Any questions out there? All right. So here again is the density of some common objects. As we talked about, water is pretty much the one you definitely should know, and that's usually the value that you use, unless it's really not sort of that temperature, and they usually find you a different value. But in most cases, 99% of the time, if you need to use density of liquid water, about 1 gram per milliliter. A reminder that ice, for example, which is the solid version of obviously water, is actually less dense, right, than liquid water. So water is a very unusual substance in that sense. It comes together in the solid phase and loses that energy and hydrogen bonds. It creates a lot of empty space between the different water molecules when it goes into the solid phase. They actually don't lock in really tight to one another. And what that does with the density of ice, for example, is it kind of bloats it and it gives it a larger volume. So if you just think about the density equation, you divide by a larger number on bottom, you're going to get a smaller density value versus liquid water when they actually it's a very unusual substance. Most substances definitely are more dense in the solid phase than the liquid phase, but water is a little bit different than that. That is why our ice cubes float, right, when we put it into our drinks. Let's finish it out here. A student needs 150 cubic centimeters of salt for an experiment. The density of salt is 2.16 grams per cubic centimeter. How many 1-pound boxes of salt do they need to buy? A conversion you do need to know, right? 1 pound is 453.6 grams, right? So take a moment or two, see what you come up with here. Trying to figure out how many boxes. Okay, so we have a 150 cubic centimeters, which is a volume. We also have the density given to us of 2.16 grams per cubic centimeter. We obviously have our density equals mass over volume. So if you weren't sure what to do, you could just kind of check off what's given to you. So clearly, it would probably make sense to solve for mass, since that's the only thing you're not given in this particular case. A reminder that you can also use density, as a conversion factor. So if you needed to, you could flip it around and do a little dimensional analysis and sort of use it like a conversion factor if necessary. So in this case, if we rearrange to solve for mass, mass is volume times density. I'm going to actually set it up a little bit like a dimensional analysis problem, so you can see the units canceling. So 150 cubic centimeters, again, going opposite here to get rid of it. We would need to use it like this, 2.16 grams per cubic centimeter. Once again, the units will cancel. That will get us 150 times 2.16, gives us about 324 grams. When we look at significant figures, really this has two, or an S, no, it has two significant figures. That's got three significant figures, which means really this should, head down to about 320 grams if we were going to use that for our answer. 320 grams is clearly less than 1 pound, so we also want to make sure that we do answer the actual question being asked, right? 1 box would be needed, and you'll have some left over at that point, right? So a couple important things. 150 only has two significant figures. Yeah, and we multiply it, right? It doesn't matter if you're multiplying numbers together, it's the least number of significant figures if you're multiplying. So in this case, it doesn't really matter if it's a volume, a mass, whatever it may be. The last mathematical step that we did was multiplying, and that 150 has two significant figures, and the 2.16 has three, and it's the smallest. So that's what you want. Yep. Other questions? All right, that wraps up chapter 2. Yeah. All right, let's go to chapter 3 here. Chapter 3 is a pretty short chapter, and it's about matter. So obviously we talked about last time the different states of matter. Matter, as we talked about, is basically the stuff that the universe is composed of. It has mass and occupied state. And as we talked about, just that opening chapter, we might have did solid, right, is the state of matter where, once again, things are really packed in there pretty tight to one another. They typically are rigid. They have a definite shape. They're hard to change because of the way that they're all packed in together. And that's a little different than in the liquid state. In the liquid state, once again, they are still relatively close to one another, but they do have a little bit more energy. So they're able to sort of one another. We think about liquids as being good. Liquids, on the other hand, do not have a definite shape, but they will take the shape of whatever container you have. But they do have a definite volume. So, for example, 10 liters of water, and I had it in a bottle, it would take the shape of the bottle. If I then trash can, it would take the shape of the trash can. If I put that water in that, where I put it. As we talked about, where essentially everybody breaks completely apart from one another. They're flying around. And again, as they're flying around, there are certain amounts of collision that's happening. Gas does take the shape of the container that it is in, and it fills it uniformly as it's flying around. It's just filling pretty much all the nooks and crannies. As we'll talk about when we get to the gas chapter, that's one of the things that makes something, as you might have heard of, or you will hear of again when we get there, something being an ideal gas. And it's the idea that we look at really the volume of the container the gas is in rather than the volume of the gas itself, because it is constantly flying around in a particular container. We talked about the idea as we transition, right, from each of these things. We got our melting, right, as we go from solid to liquid. Liquid back to solid is our freezing. We have evaporation on my big line there, our vaporization. As we go from liquid to gas, heading backwards again, gas to liquid is condensation. And we also can go from solid directly to gas, which is our sublimation. And gas, again, skipping the liquid part, directly to solid, which is our deposition. We talked about, I think, as well, a little bit about the energy component to that. And again, the energy component is as we go from solid to liquid to gas, energy is being absorbed. And that is what is known as being endothermic. Again, if you take something like an ice cube, as we might have talked about, and it picks up some energy, or you heat it up, it'll go liquid water, take liquid water and continuously to heat it up, it will become steam. And vice versa, as we go the opposite direction, gas to liquid to solid, energy is released in those cases. And that is what is known as being exothermic. And that is why when something, for example, gets into the solid phase, it has lost a good amount of energy. It doesn't have a lot of energy, and that's why everybody just kind of locks in on each other. They don't really have enough energy to move from each other, and they come into a really solid phase. To as you gas side, they gain a lot of energy, which is why they're able to really break apart from one another, start flying around, and it requires obviously a lot of energy to do so. So obviously here's some different liquids, and obviously we'd have perhaps the same volume, but it does take the shape of whatever container it's in. One of the few exceptions, as we sort of talked about there with density, is water. Water has sort of an unusual property, as I mentioned before. It's in a solid state than it is in its liquid state, which is unusual. And that's because talk about in several points because the oxide water is actually more negative than the hydrogen side. When two waters get together, they do what is referred to as hydrogen bonding, which is basically a bond between the hydrogen in one water and the oxygen in another. Uh, that is a basic theme of chemistry, is the idea that opposites attract, right? So much like in life, two positive people, nobody wants to be near each other. That's just too happy. Two negative people, bummer for everybody, right? But you find like a happy person and maybe a negative person, they balance each other out. And the same thing happens in chemistry. Things with opposite charges, positive and negative things, are attracted to one another. Things that have the same type of charge do not want to be near each other. They're repelled by each other. So things that are positive charge will actually go in the opposite way. So how molecule interacts with itself, other molecules, attraction, which is sometimes referred to as electrostatic attraction, positive and negatives being attracted to each other. So as I was mentioning before, you can see in the solid state, as these water molecules try to get close to each other, creates all these open sort of pockets in the structure. And again, that is why, as I mentioned a second ago, that when we look at the density of it, is much larger volume than you can see happens here in this liquid state, where those water molecules are still able to kind of get a lot closer to one another. And again, that accounts for why we see a smaller density for water. The states of matter depends on the strength of the forces that hold them together. The stronger the force is, the more likely it's going to be a solid. That also accounts for sort of that interaction between a molecule and itself, like water and water, which is sometimes referred to as intermolecular forces, which we'll talk more about in a later chapter. And these are the forces that hold one molecule together with another. And in the case of water, that's the hydrogen thing we're talking about. So the stronger those forces, most likely that thing will be a solid. The weaker those forces, most likely that thing will be more like a gas. So for example, water is a pretty strong force, and in most cases, water is found in the liquid state. But something like methane, which is what the gas comes out where you light your Bunsen burner, that's held together by a super weak force, very, very weak force. And that's normally found as gases. A lot of organic molecules, for example, are found as gases under normal conditions, things like methane, propane, butane, right? These are all the things we use to barbecue with and light fires, basically. And that's because those things can go into the gas phase really easily. Something that is volatile, by the way, can go into the gas phase really, really easily. And a lot of organics are like that, which is why they make you work in a fume hood when you take organic chemistry, because very often whatever you're working with can go into the gas phase very quickly, and it can be flammable. And you do not want to have any type of flame. Yes, no type of flame. If it's something that's flammable, out. Activity question, yes. So no flame, small flames enough to set something on fire as well, by the way. So no flame should be out. Yeah. We really don't include it because these are the three kind of normal states that, most of the time that we come across. All right, so these are just in your book that's over some of the things that we talked about: solid, which again is rigid, has a fixed shape and volume. Liquids have a definite volume, takes the shape of the container, and obviously our gases have no fixed volume, but does fill the container uniformly. So let's talk a little bit about physical properties and chemical properties and physical and chemical changes. A physical property is a property that can be measured without any change to the composition or identity of it. Typical physical properties: volume, state, is it solid, liquid, or gas? Density, melting, and boiling points as well. And melting and boiling points, for example, are affected by how strong the attraction forces are between, say, one molecule itself. The weaker the attraction between a molecule and itself, the lower you would have in each of them. Physical properties are associated with and when we have a physical what we start with and what we end with is fundamentally the same thing. So, for example, if we take something like water and I have an ice cube, which is H2O, and I melt it down into liquid water, that is still H2O, right? And if I heat up the liquid water and I create steam, that steam is still fundamentally H2O. In all those states, they are all still water. They have not changed into anything new. And those would all be physical changes. So as you change states, those are all only physical changes. It's just the appearance of it. You know, if I had a peanut and I crushed it up, still a peanut, just in a lot more pieces that I started with. It didn't fundamentally change like a carrot or anything like that, right? Still going to still be peanut, stuff like that. The important part about a physical change is whatever you start with and whatever you end with fundamentally is still the same thing. It may just have a different appearance, but nothing has sort of reacted, and it's going to be the same thing all the way through. So as I mentioned before, the water is a very common example that people sometimes mess up on. But just changing the physical property of that substance. It is not changing into anything new. Yeah. It can change. It can change. Some substances can change some properties depending on the state that they're in. So, for example, if you had solid sodium chloride, for example, it will not conduct electricity. But if you dissolve sodium chloride into water and make a solution of sodium chloride, for example, that would be something that would conduct electricity. Yeah, so. It would still be a physical change, yeah. So when you make something like, say, like a solution, it's really just a physical change that's happening, yeah. Other questions? Now, a chemical property which is associated with a chemical change is basically something that the property of a substance, how it does change chemically, or it actually can resist some type of chemical change. And example, a chemical change, the difference is what you start with and what you end with are two different things fundamentally. And the important part of that is you cannot get back what you started with by any type of physical things, like freezing, boiling, stuff like that. Yeah. Yeah, so really chemical properties really relate to the substance ability either to actually go through a chemical change or resist a chemical change. That's usually sort of like what the chemical properties is. And the way that you sort of know, is kind of think of it as is something reactive or not reactive is sort of like what you look at in terms of that. And the way you oftentimes will sort of measure a chemical property is whether or not you kind of get a chemical reaction that sort of occurred. And that is basically what a chemical change is. A chemical change is basically a chemical reaction that occurs. So, for example, the formation of rust. In order to make rust, united together, you can do whatever you want to that rust. You could either back or the oxygen back through any type of physical means. So anything that is a chemical reaction basically is a chemical change. Just like when we digest food, right? It all breaks down chemically, right? In our bodies, we use different parts for different things to keep our bodies going. There's no way to get that food back, hopefully, right? In the way it came after it's obviously been digested. So another example is hydrogen gas and oxygen gas will form water. So hydrogen gas plus a little bit of oxygen will make some water, do a little balancing like a good chemistry person, I suppose. And we'll have this reaction that will occur. Water, you can do whatever you want to it, right? Boil it. You will not get the hydrogen gas back or the oxygen gas back. Otherwise, when you went to go make pasta and you boil that water, you would never get to the pasta making part because it would probably explode from the hydrogen gas, oxygen gas that you would generate. So you cannot get back the gas in their normal means. You absolutely could, if you wanted to, run an electrical current over the water, which you'll do in one of these experiments, I think. You ran an electrical current. And that would be enough to cause a chemical reaction to occur and actually break it back down into the hydrogen gas and oxygen gas. But that would require chemical reaction to occur. Or very water, which the hydrogen and oxygen are together. Any questions on that there? Yeah. Chemical change, yes.
The water is the new substance, right?
Yes. Yeah, so the formation of a new substance usually involves some type of chemical reaction, and that's a chemical change that occurs. Obviously, a couple other examples here, hard-boiled egg changes everything after you heat it chemically. And again, after you eat it, we will break that stuff down along the way. So when we talk about physical changes involve really nothing fundamentally changing. Again, what you start with and what you end with is still really the exact same thing. May have, again, some different type of appearance. Most common, again, physical changes that we see is really the changes of state as we go to liquid to gas and backwards. Those are very, very common changes. That chemical change does require something to fundamentally have changed. And again, is, you really can't get back those original substances through any type of the physical means, which again would be something like freezing, melting, of that nature. Again, chemical changes are chemical reactions. Another example of that is silver tarnishing by reacting with substances, and that's pretty much when metal coating on something like that. Those are all type of reactions that occur. Those are all chemical changes that actually occur. And to speak to your question earlier, when you do something like that, for example, when you plate a metal where it's like a protective layer, you are changing sort of the properties of that metal because it will change sort of the, say, reactivity of that metal and stuff like that. Yes. Pretty much, there's a bunch of chemical reactions we're going to talk about in a later chapter, but there's synthesis reactions, decomposition reactions, combustion reactions, single replacement reactions, double displacement, redox reactions. So, anything that results from like two things making something or one thing breaking down into something else. There's a decomposition reaction, for example, where you make something like carbonic acid and it very quickly makes CO2 and water, like the plop plop fizz fizz Alka-Seltzer type deal. That's sort of the type of reaction. So there's, as we'll talk about in that chapter, there's kind of two big categories of types of reactions that occur, and underneath them, there's a lot of specific individual types of reactions that occur. All right, so let's talk a little bit about elements and compounds. An element is really the basic unit of everything. It can be found on the periodic table, as we will talk about. Charge and neutrons, which have no charge, makes up an atom. You could think of an atom as sort of a bit. It is, we have a certain number of elements that are present. Different combinations of different elements will create what are sometimes referred to as compounds. And compounds are a combination of two or more atoms of different elements. Now, there is sort of a word that sometimes people get confused with compounds, and that is the idea of molecules. And molecules are the combination of two or more atoms. So they have very similar sort of definitions, and a compound has to actually be made up of two different elements, at least two different elements. A molecule does not. So for example, there are certain elements that the way that they naturally come is that they come as molecules. So things like hydrogen comes as two hydrogens, oxygen, nitrogen, fluorine, chlorine, bromine, and iodide. These all come as what is referred to as diatomic molecules. The way that we find hydrogen in it by itself, uncombined, is as two hydrogens basically bound together, a diatomic molecule. Each of these things, hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine, they are all molecules because they are made up of two or more atoms together. They are also all elements because in hydrogen, there's only hydrogen atoms present, right? They're all hydrogen, just like if you had oxygen, in oxygen, there's only oxygen present. So oxygen is an element. Oxygen is also a molecule because it's made up of two or more atoms. Yeah. A lot of them, not all of them, but a good majority of them in terms of the diatomic elements are gases like hydrogen, oxygen, nitrogen, fluorine. Chlorine's a gas. If you look at bromine, it's kind of like a gas with a vapor over it. And then I2 is more of a gas or solid type of thing. So a good majority of them are gases. And that's what's a lot of those guys kind of share in common. Now, is hydrogen, oxygen, fluorine, chlorine, bromine, is it a compound, these guys? They are not compounds because they are only consist of one element. So that's an important distinction. Now, if you had something, say, like water, water is a molecule because basically it has two or more atoms together, right? If you drew water, it looks something like this. Water is also a compound because it has two or more atoms of different elements together, hydrogen and oxygen. Is water an element? Water is not an element. So water is not an element. So molecules you could think of as a do I have two or more atoms together? Doesn't matter if they're the same or different. That's basically what a molecule is. A compound is I got to have at least two or more atoms, and I also has to have at least two or more elements involved. So that is the difference between those two. Any question? By the way, elements, like I said, are like the alphabet. You can kind of do different mixtures of different elements, gives you different compounds along the way. Elements are as far back as you could go. So for example, you can take a compound and break it into its elements. And again, you cannot go any further than that at that point. So the example like we just looked at, which was water, you could break down into hydrogen gas and oxygen gas into its elements here, a compound. But you cannot go any further. You can't break those guys down any further. Most elements on the periodic table are what are referred to as being monoatomic, mono meaning one. Again, guys that we make di meaning two atoms, basically, and so forth. So a compound is a substance, again, composed, as I mentioned, of two or more elements that are united in fixed proportions. They always come the same. So what that means is no matter where you find your water, it should always be H2O. Just might cost you more depending on how it's bottled and given to you. But it is ultimately just H2O that is in there. It will have the same proportion no matter where it is. So we'll always have two hydrogens, for example, to one oxygen. It will also have the same ratio of mass, right? Because it should always have the same number of hydrogen and oxygen as well. As I mentioned before, through some type of chemical means, like a chemical reaction, you can definitely break down compounds into the elements. But once again, once you get to those elements, that's again as far back as you can go. It's also really important. You do need to know, obviously, those diatomic molecules, the hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And you got to remember that they do come as twos. And that's really important when we get into things like writing chemical equations and stuff like that. People oftentimes, when they have like hydrogen and they got to like write the formula, they'll just write H and you'll have the wrong formula. You won't be able to balance the equation. So again, it's important to just keep that in mind. The common error a lot make when they deal with those diatomic elements. As I mentioned, again, always has to have those different elements involved. Carbon dioxide, which is CO2, looks something like this, is a compound. It is a molecule once again as well, and it is not an element in this case. Now, the properties of compounds are usually very different than think about sodium chloride, for example, salt. Sodium is a soft metal. Chlorine is chlorine gas, which is a toxic green gas. But through the miracle of chemistry, when they come together and they make salt, we throw it on our fries, right? And has very, very different properties than each of the individual elements to make them up. Same thing with hydrogen and oxygen, have very, very different properties in their sort of state by themselves than in, say, water, right? So a lot of times compounds will have very different. Yes, sir. Yeah, so like I said, a molecule is really, it's just kind of like a basic definition. You can think of it. All you have to meet is there two or more atoms? And again, they could be two or more of the same element or two or more different elements. A compound, it takes it one step further that it has to be two or more atoms, but it also has to be two or more elements involved. So that's the sort of additional part of it. All right, let's talk a little bit about mixtures and pure substances. A substance is the form of matter that has a definite composition. The number of units that are present. So for example, if you have a pure substance of just water by itself, it should be just water, nothing else involved. If you have ammonia or sugar, if you have some gold, which would be good, I imagine, that is just a pure substance by itself. Substances differ from one another. Appearance, taste, and smell. So water tastes different than sugar, I suppose. This is a good example. We won't use ammonia. Ammonia, by the way, smells very different than water. Like you think about Windex or something like that. But Gold obviously looks very different than, say, sugar or something like that. They try to trade that in. Here's my gold. Is that sugar? Yeah, it doesn't look the same. Now, a mixture is a combination of pure substances where each substance will actually retain their own identity. So if you take water by itself, that is a pure substance. If you take sodium chloride, that is solid. That also is a pure substance. If I combo those guys together and put my sodium chloride into my water, the sodium chloride or the salt will dissolve in my water, and I will make a sodium chloride solution, which will have the aqueous symbol next to it, and that means aqueous. It basically means a solution or a water environment. Sodium chloride is a mixture. A sodium chloride solution is a mixture of both of those things, the water and chloride together. Now, regardless of the type of mixture it is, everybody still retains their important part of making it a mixture, an important part of their identity. So let's talk about the two different types of mixtures there are. The first type of mixture, a homogeneous mixture, is called a solution, and those are typically things that have the little aqueous symbol next to it. In a homogeneous mixture with sufficient mixing, everything will look the same throughout. So it'll all just look like one layer or something, to one phase, like the sodium chloride in water. If I take some salt and put it in my water, when I do that, it just looks like water at that point, right? You don't see the salt. If you grab some water from the ocean and nothing else floating in the ocean, you just grab some water. It just looks like water, right? But if you taste it, it's like, whoa, that's a lot of salt in there. So same thing with sugar. If I took some sugar and I put it in water, it's going to dissolve the sugar and it will just look like water. So homogeneous mixtures, everything sort of mixes really well. When you look at it, it looks just like one thing there, still there in that particular mixture. Heterogeneous mixture, on the other hand, a heterogeneous mixture is a mixture where even after sufficient mixing, you will still see, for example, if I did take, like you're going to do today, I'll just make my sand red. If I took some sand in that water, I can mix that all day. That sand is dissolve in the water or anything like that. You will still visually be able to see it. Same thing if you took some metal pieces and you put it into the water, as long as it's not reactive with water. Or maybe a better example would be if you took some metal and put it in sand and put those guys together, you still be able to see the metal pieces definitely is there. So a heterogeneous mixture is the idea that we still see these different layers, regardless of how much mixing goes on. Homogeneous, we still see everything looking as one layer. Now, regardless of what type of mixture you have, be it a homogeneous mixture or a heterogeneous mixture, you can still separate out your components by some type of physical mixture by a physical mean. And that could be boiling, which is taking advantage of differences in boiling points or physical properties, so forth. So if I could get back all the original parts of my mixture, is making a mixture a physical change or a chemical change? It's a physical change. So although when you dissolve, think like a chemical change just occurred because you can't see it anymore. It is still there. So for example, a couple of ways to separate out things when you have something like, say, we'll do our sand and water mixture. And again, that is a heterogeneous mixture. A good way to do that is through a process known as filtration. So you take a really badly drawn funnel and you put a piece of filter paper up there. And when I take my sand and water mixture and dump it through here, perhaps put something underneath the catch, my liquid part, right, the water part should go through, right, and be collected, say, in the beaker here. All my sand should get caught up there on the filter paper because it's too big to go through the small holes that are actually in the filter paper that you can't really see. And it gets dropped there. By doing this simple process of filtration, I have now just separated out both parts of that mixture. I could let the sand dry, right? And it'll be just like it was when I started. I could obviously collect all the water and I have both parts of my mixture back out. Thus, nothing has fundamentally changed. The sand was still there, the water was still there like it was before. Again, that is why it's a physical change and not a chemical change that is going on. I could even do that. Obviously, this is filtration. Could also do that with my saltwater example, right? And my saltwater is obviously a homogeneous mixture. And again, with the salt water, you really can't see the salt at all, right? It's gone. Chemical reaction sometimes. But if I took the salt water, for example, and put it into this apparatus, which is horribly drawn, we'll see a much better picture in just a second. But we'll put my salt water over here and we're going to keep it in a closed container. This guy right here is going to be kept really cold, this kind of connecting tube from one side to the next. And I take my wonderfully drawn Bunsen burner, which is also known as a triangle and a line there and an arrow, and I start to heat my salt water, right? As I start to heat my salt water, what happens to my salt water? The water part starts to evaporate, right? So the water part will start to evaporate, which will create steam. And that steam has nowhere to go, but it's going to go through this really cold container here, our tube. And when we have steam, which is the gas phase, and you cool it back down, it goes through the process of condensation, right? And out on the other side, it's going to drip, right? And you will be collecting your water on the right-hand side here. Continue to heat it, right? Right? Gone. And you will be left with just the salt at this point. And you have successfully through this process, which is known as distillation, have separated out both the salt component, which you couldn't even see in the picture, and the water component in their original form. Once again, you can salt back out. You're going to do basically a version of this, except you're going to use an evaporating dish in lab. And you're going to put it up there and heat it, basically. And what you're going to do is you're just going to let the water component go off as steam. You're not going to collect it, right? And if you do that, eventually what will happen in your evaporating dish, you'll have the solid residue that will be left over. And again, mix it, right? Yeah. No, well, a solution, which is what these are, right? So a solution, there's actually two parts to a solution. That's the solute and the solvent, actually. And the solute is the smaller part of the solution, and the solvent is the larger part of the solution. So in the case of something like salt water, the salt would actually be the solute dissolved in it, and the water would actually be your solvent. So you would solvent in this case. Your filtrate and is usually like when you do filtration, like the previous slide. What comes through is the filtrate, the liquid part. The liquid part is sort of the precipitate that's left over. Now, those are the two methods, distillation and filtration. And again, filtration is a really good way to separate a solid from a liquid. Again, regardless of the type of mixture, homogeneous or heterogeneous, you're able to do that. And it's all just a physical change. that's occurring. You're actually taking advantage, as I mentioned, physical properties, the difference between the physical boiling point of the water and the boiling point of the salt. The salt is an ionic compound. It's actually held by probably the strongest attraction you have. And if you have salt by itself in a solid state, you could heat the heck out of it. I'll choose the right word there. You heat the heck out of it, and it will never go into the gas phase. It's held together so strongly, it'll just start melting. But water, you just need to get it up to 100 degrees Celsius, and we know that it will start to boil, right? And then go into the gas state at that point. So when we do something like distillation, or when you do something later today, like your evaporating dish, what you're actually doing is taking advantage of different physical properties of those two substances in that mixture. And because water only needs that 100 degrees Celsius to get it to go into the gas phase, we're able to get them away from each other in a mixture where if you look at it, you can't even see the salt water. Why is it still there? Has a little bit to do with some stuff we'll talk about in a later chapter, but essentially salt, like sodium chloride, when it goes for a swim, are two ions that are present. And the water, as I mentioned before, is a polar molecule. It has a negative side and a positive side. What happens is when you go to dissolve something, the negative side of water is attracted to the positive ion, like the sodium ion, for example, and it will surround that sodium ion with a ton of waters. The negative guy, like the chloride ion, is attracted to the hydrogen side of water, which is the positive side, and it will also surround those ions. So water works really well to dissolve ionic compounds because of this opposites attract. As the hydrogen is more positive, there's an attraction. Oxygen is more negative, attraction there. And what happens is there's so much water around each of these, that was the sodium chloride, you no longer could visually see that it is still there. You could only see it's there when you start to heat it, because as you start to heat it, it knocks off all these water molecules around them. And now there's no water molecules to keep those guys separated. They will come back now into their solid state like an ionic compound will be, and you'll be able to see it occur again. So this is why sometimes when people look at or say like salt water, they go, oh, it's a chemical change. Like, I don't see the salt anymore. It's gone. But it actually is still there. You just can't visually see it. And it's still there in its original form. You just can't visually see it. And again, this is why it's a physical change. Any questions on that? So here's a picture of a proper distillation apparatus, which again, if you close your eyes and didn't look at my drawing, looks exactly like this. But here's again, taking that difference of physical properties, boiling our salt water, going through this cold tube here. Out comes our water, our pile of salt left over at the end. And again, we have successfully separated out both of the mixture. So mixture take-home message, two or more just together, where they do retain their identity, making it really a physical change that's occurring. And because it's a physical change, you can use physical properties of those substances, like boiling point differences, melting point differences, to separate out things. Also physical properties like size as well, right? And that's what filtration does. Filtration separates out the solid, which is much larger than the water molecules, and the water molecules are able to go through the filter paper holes. The solid is too large to go through the filter paper holes. So again, that difference in physical properties of those two parts of the mixture and something like the sand, which is a head using filtration, is how we're separating those guys out as well. Either be an element or a compound. So again, you could have gold by itself, which is a pure substance. You could have sodium chloride, which is a compound that's a pure substance. And once again, compounds can be broken back down into elements. But again, that is go, also known as chapter 3. Yes, any questions there? All right, good place.